Welcome to example number 3 in another ideal gas law type of problem. So we have a piston that applies a constant pressure on a volume of 1.78 meters cubed that is an ideal gas, and that ideal gas is at a temperature of 20 degrees Celsius in the piston. Let's just show a quick little picture of this scenario initially. So there we have a piston here with a platform that can move up and down. It is of constant pressure, which means that this platform can easily slide up and down without any friction along the sides, and the pressure is due to the weight of the platform and all the air pushing down. So as long as this can move up and down, then this pressure will remain constant. So we have a constant pressure P1, we'll just simply call P. The initial volume of the gas in here, so we have all these molecules in here, V1 is given as 1.78 meters cubed, and we're also told the temperature at the initial state is 20 degrees Celsius. Okay, we now know that if the temperature of the gas is increased at 80 Celsius so that the platform can move up and down, it'll change volume under this constant pressure process. How does the volume change? Can you think of what would happen if you were to increase the temperature? Remember, these molecules are now moving a lot faster and bumping into the walls. What would happen to the volume? Hopefully you'll realize that the volume will expand because the volume is directly proportional to the temperature when the pressure is constant. So let's show a picture of state 2 now. So now you can see the volume is expanded to the same pressure, pressure 2, we'll just simply call P. Volume 2 we don't know, we're looking for that in meters cubed, and then the temperature 2 is now 80 degrees Celsius. So this is a problem that involves Charles' law. Why? Charles' law says over here that if you can have a constant pressure process, the volume is directly proportional to the temperature. Now there is one important thing that you need to realize is that the volume, pressure, and temperature need to be in appropriate units. Let's take a look at that. All right, first we'll develop the formula in a minute here. We have, I'll just write down ideal gas law. PV equals nRT, and then we'll write it once more. PV equals nRT. And then we'll write it for state 1, P1, V1, and T1, and then pressure 2, volume 2, and temperature 2 for state 2. And then we'll cancel out the things that we know that are constant from state 1 to state 2. So the number of moles in state 1 and state 2 is the same because there's no leak, there's no gas that's actually escaping, and the gas constant is constant as well. And then the pressure is remaining constant because the platform can move up and down, so pressure 1 and pressure 2 are the same. And we get volume 1 over volume 2 equals temperature 1 over temperature 2. And then we now need to start substituting in. However, there is a very typical mistake that people make at this juncture in time. What do you think it is? Common mistake is that people forget to convert the temperature to Kelvin. The temperature T must always be an absolute temperature. Means that if you're given a temperature in degrees Celsius, you have to add 273 to convert it to Kelvin. So this temperature 1 is 20 plus 273 Kelvin. So you really have 293 Kelvin. And then we have over here 80 plus 273, which is 353 Kelvin. And you need to do that first before you substitute. If you had left it as 20 and 80 Celsius, you'll definitely get the wrong answer. The temperature looks like it quadruples, but on an absolute scale, it is not really quadrupling. It's going 353 divided by 293. So always, always, always remember that your temperature must be an absolute temperature. Or absolute Kelvin. So you have to, the reason for that, by the way, is that when you get to, say, 0 Kelvin, it should also be 0 pressure and 0 volume. Okay, so volume 2 is what we're looking for. So let's rearrange this equation. It will be temperature 2 to temperature 1 ratio multiplied by the initial volume 1. So temperature 2 is in Kelvin, 353 Temperature 1 in Kelvin is 293 Kelvin, and then the volume 1 is 1.78 meters cubed. And this gives you an answer of 2.14 meters cubed. So remember that the temperature must be the absolute temperature in Kelvin, not degrees Celsius, not degrees Fahrenheit. And also remember too, when we deal with problems where you're given pressures, the pressure must be an absolute pressure, the total pressure. If they give you a pressure in gauge pressure, for example, you need to convert that to the absolute pressure. Okay, you ready to do now the next example?